way down to the fundamental properties of the universe.
Yeah, the real bedrock stuff.
And we're tackling something that sounds simple but is actually pretty counterintuitive: electric charge. Specifically, the idea that it comes in tiny, indivisible packets.
It's a fantastic topic. We've been looking at this analysis of particle charge quantization, and it's just, well, it's a core feature of reality.
Right, and our mission here is to unpack that. What does quantized really mean in this context? How do we figure it out?
And we'll get into the whole journey, the experiments, the particles involved, and even a bit of a twist with some particles that seem to break the rule, but don't.
Exactly. We want to understand the why behind it too, or at least the theoretical attempts to explain it. So yeah, get ready for some real aha moments.
Definitely.
Okay, so let's dive right in. Charge quantization, what's the basic idea?
Think of it like money.
Yeah.
You've got pennies, nickels, dimes, dollars.
Yeah.
Specific units.
You can't just have, like, pi cents.
Exactly. Charge is like that. It's not a smooth, continuous thing where you can have any amount you want. It comes in discrete lumps.
So there's a smallest possible charge quantity.
Precisely. We call it the elementary unit of charge, usually written as E.
Okay.
And the fundamental rule, at least for every observable free particle we've ever found, is that its total charge is an integer multiple of this E.
Meaning plus 1m, -1m, plus 2e, -3e, something like that.
Yep, or 0e, of course. But you just don't find a lone particle casually floating around with, say, plus 0.7e or -2.1e charge. It's always whole numbers times e.
That's actually pretty weird when you stop and think about it. It's not obvious. How did scientists even land on this?
Oh, it wasn't obvious at all. It took decades. The very first clues, believe it or not, were way back in the 1830s. Michael Faraday.
Faraday. With electrolysis, like running current through water.
Yeah, exactly, that sort of thing. He found that the amount of chemical change, like how much stuff pleated onto an electrode, was directly proportional to the total charge passed.
So charge seemed linked to discrete amounts of stuff, like atoms.
It suggested that, yeah, it hinted that maybe charge carriers were tied to these individual chemical units. A subtle clue, but a start.
Okay, a hint, but not proof that charge itself comes in packets.
Right, not yet. The next huge leap was J.J. Thomson in 1897 discovering the electron.
Ah, the electron. A specific particle with negative charge.
Yes, and he measured its charge-to-mass ratio. That was massive, identifying a fundamental carrier of negative charge. But still, it didn't prove charge only exists in electron-sized chunks. Maybe there were smaller bits.
So who finally nailed it? The definitive proof?
That was Robert Millikan. His oil drop experiment, running roughly from 1909 to 1913, that was the clincher.
Right, the oil drop experiment. I remember learning about that. Super clever. Tiny drops of oil.
Tiny drops sprayed into a chamber. Some get charged, maybe from friction, or sometimes he'd use X-rays to knock electrons onto them.
Okay, and they're between two metal plates.
Exactly. With a voltage across the plates, creating an electric field.
So the field could push or pull the charged drops, balancing out gravity.
Precisely. He could adjust the voltage very carefully to make a specific droplet hang perfectly still, or fall or rise at a known speed. From the droplet's estimated mass and the strength of the electric field needed to balance it, he could calculate the total charge on that single droplet.
And he did this for thousands of drops, right? What was the pattern?
This is the absolute core finding. The charge he calculated for every single droplet was always, without fail, a simple whole number multiple of a certain minimum value.
Always, like 1 times this value, or 2 times, or 3 times.
Or -1, -2, -4, but never 1.5 times, or 2.7 times, or 0.8 times that minimum amount.
Wow, so that minimum value had to be the fundamental packet.
Yes, that was E, the elementary charge. Millikan's experiment was the direct, undeniable proof. Charge is quantized. It comes in these E-sized units. And he measured E's pretty accurately, too.
What's the value again? It's tiny.
Super tiny. About 1.602 times 10 to the minus 19 coulombs. A minuscule amount of charge, but it's the fundamental building block.
Okay, so experimentally proven. Charge comes in packets of E. How does this play out with all the different particles we know?
Well, the most basic examples are right there in the atom. The electron has charge E. The proton in the nucleus has charge plus E.
And things like muons, tachus, other fundamental leptons.
They also carry charges of plus E or EO, always integer multiples.
What about bigger things, like atomic nuclei?
Simple addition. A nucleus is made of protons and neutrons. Neutrons have 0 charge. So the total charge is just the number of protons times plus E. Helium nucleus, 2 protons, charge plus 2e. Uranium, 92 protons, charge plus 92e.
Straightforward. And ions, like when salt dissolves in water.
Same idea. An ion is just an atom or molecule that's lost or gained electrons. Lose 1 electron, you're left with a net charge of plus e. Gain 1, net charge e. Gain 2, next to e.
Because you're literally adding or subtracting these indivisible e packets carried by electrons.
Exactly. It all fits perfectly. The charge on ions is always an integer multiple of e.
You know, one thing that always struck me is that the proton's positive charge is exactly the same magnitude as the electron's negative charge, plus e and e. Not like plus e and met us at 1.0001 e.
That is unbelievably important. One of those amazing fine-tuned facts about the universe. This perfect balance is why atoms can be electrically neutral overall.
Equal numbers of protons and electrons, charges cancel out.
Right, and that neutrality is essential for, well, everything. Stable atoms, molecules forming, chemistry, life. It all relies on that precise charge equality.
Okay, so the rule seems rock solid. Observable, free particles always have integer multiples of E. Seems settled, but I sense a but coming. There's a twist, isn't there, when we look inside protons and neutrons?
Ah, yes, the twist. When physicists started probing protons and neutrons really deeply, they found they weren't fundamental. They're made of smaller things.
Quarks.
Quarks. And here's the shocker. Quarks have fractional electric charges measured in units of E.
Fractional.
Right.
Like not whole numbers.
Correct. There are different types or flavors of quarks.
Yeah.
The up, charm, and cop quarks all have a charge of plus E.
2/3.
2/3.
Right.
And the down, strange, and bottom quarks have a charge of E.
Minus 1/3. Hold on. How does that work? We just established everything comes in units of E, and now the building blocks themselves have fractions. Doesn't that break the rule?
It really looks like it breaks the rule. It's a major puzzle. How can you have building blocks with E charge if you only ever see multiples of 1m in the wild?
Yeah.
The resolution comes from another fundamental aspect of particle physics, the strong nuclear force.
The force that holds quarks together inside protons and neutrons.
Exactly. It's described by theory called quantum chromodynamics, QCD. And this strong force has a very weird property called color confinement.
Confinement, meaning the quarks are trapped.
Essentially, yes. The force between quarks behaves strangely unlike gravity or electromagnetism. It actually gets stronger as you try to pull them apart.
So you just can't pull a single quark out on its own.
Under normal circumstances, no. They're permanently confined inside composite particles called hadrons, like protons and neutrons. You can't isolate a free quark to observe its fractional charge directly.
Okay, they're trapped. But how does that fix the charge problem?
Because the combinations of quarks that are allowed to form stable hadrons always add up to an integer multiple of E.
Always. Let's check. A proton is 2 ups and a down.
Yep. So charge-wise, that's plus E plus E plus E.
Okay. U plus U is 43. Minus U is 33, which is 1.
Exactly. Plus 1E. Integer charge for the proton.
Mind blown. Okay, what about the neutron? That's 1 up, 2 downs.
Right. So plus U plus E plus...
Oh, let's see. U minus U is U minus another U is 0.
0 charge. 0 U integer again.
Wow. And this works for all the hadrons we see. Mesons, too, which are a quark and an antiquark.
It does. Take a positive pion, pi plus here. It's an up quark and an anti-down quark.
And anti-down. Antiquarks have opposite charge, right? So anti-down is plus U.
Correct. So the pi plus is plus U plus U.
That's 33. Plus 1E again. It always works out to integers.
It always works out. So the fractional charges are real. They exist inside these particles. But because of confinement, you only ever get to see the combined packages. And those packages always obey the integer charge rule relative to E. The twist is resolved.
That's really elegant, actually. Nature hides the fractions inside integer boxes. But it still begs the question, doesn't it? Why is charge quantized at all? Why this E? Is it just a random rule, or is there some deeper reason physics points to?
Ah, the why question.
Yeah.
That takes us into the realm of theoretical physics. And there are some really profound ideas. One of the earliest and most famous arguments came from Paul Dirac back in 1931.
Dirac again. What did he propose?
He was thinking about magnetic monopoles.
Magnetic monopoles, like just a North Pole or just a South Pole all by itself. I thought those didn't exist.
Well, we've never definitively found one, but Dirac showed that if just one magnetic monopole exists anywhere in the universe, then electric charge must be quantized.
Whoa, hang on. How does a hypothetical magnetic thing force electric charge to come in packets? That connection seems unexpected.
It comes from the maths of quantum mechanics. Dirac looked at how the quantum wave function of an electric charge, like an electron, would behave if it moved near a magnetic monopole.
Okay.
For the quantum mechanics to be mathematically consistent, for the wave function to make sense everywhere he found a condition had to be met. The product of the electric charge, let's call it Q, and the magnetic monopole's charge, G, had to be equal to an integer times a fundamental constant.
Which constant?
It involves Planck's constant and the speed of light, basically 8 times an integer, or half integer depending on convention. So Q times G has to equal n times some constant.
Okay, QG equals integer constant.
Right. Now, if you assume a monopole exists, G is not 0. For that equation to hold true for any allowed integer n, the electric charge Q cannot be any value. It must come in discrete steps, proportional to that constant divided by G.
So the mere possibility of magnetic monopoles forces electric charge into quantized steps.
According to Dirac's argument, yes. It's an incredibly powerful theoretical link. Even though we haven't found monopolies, their potential existence provides a deep reason for charge quantization within quantum mechanics.
That's fascinating. A potential answer locked away with a maybe particle? Are there other theoretical angles?
Yes, definitely. Within our current best theory of electromagnetism, quantum electrodynamics, QED, quantization is usually put in by hand based on experiment. But the structure of the theory itself hints at it.
How so?
QED is a type of theory called a gauge theory, based on a mathematical symmetry group called U1. For the theory to work nicely, especially regarding how charges are conserved, this U1 group needs a property called compactness.
Compactness sounds technical.
It is a bit abstract, yeah. Think of it like a circle versus an infinite line. A circle is compact, you go around and come back. An infinite line isn't. The mathematical consistency of QED seems to require this U1 symmetry to be like the circle. And that property, compactness, naturally leads to the charge associated with that symmetry being quantized.
So the very mathematical framework of QED prefers charge to be in packets.
It seems deeply connected, yes. And then there are even more ambitious theories. Grand unified theories, or GUTs.
Those are the theories trying to combine electromagnetism with the weak and strong nuclear forces, right?
Exactly. Trying to show they're all different aspects of one single unified force at extremely high energies.
How do GUTs explain charge quantization?
In many GUT models, particles that seem very different to us now, like quarks and leptons, electrons, neutrinos, are actually grouped together in the same fundamental family or representation under the bigger GUT symmetry group.
Okay.
When that big symmetry breaks down into the forces we see today, the mathematical structure of how it breaks dictates the allowed charges for all the particles in that family. It doesn't just allow quantization, it often predicts specific relationships between charges.
Like, it could explain why the down quark has exactly the charge of the electron.
Precisely. The structure of the unified group can force these specific fractional relationships, which then combine to give the integer charges we observe. Quantization, and even the charge ratios, can emerge naturally from the attempt to unify the forces.
And I think the notes mention string theory, too.
Briefly, yes. The analysis we looked at mentioned that in string theory frameworks, charge quantization also tends to pop out naturally. It might be related to how the fundamental strings vibrate, or how extra dimensions are curled up or compactified.
So it seems like quantization isn't just some weird experimental fact, but something that keeps showing up in our deepest theoretical attempts to describe reality.
That's a good way to put it. It feels fundamental.
Okay, let's zoom back out. What's the big picture takeaway, this significance of charge coming in these E-sized packets?
Well, as we said, it's absolutely essential for the universe as we know it. That precise plus E on the proton and E on the electron allows for neutral atoms.
Which allows for chemistry, molecules, stability, basically everything.
Everything. Without quantization, and specifically that precise equality, matter just wouldn't organize itself the way it does. It's also fundamental for the consistency of our theories, like QED, and seems baked into ideas like GUTs.
So it's experimentally solid, theoretically supported? But are there still mysteries? Loose ends?
Oh, absolutely. We have compelling arguments and observations, but the ultimate why. Why this structure? Why the U1 group for electromagnetism? And why is it compact? Those are deeper questions about the fundamental blueprint of the universe.
And there's one more really nagging question, isn't there?
Yes. Why does E, that elementary charge, have the specific value that it does, that 1.602 by 10 coulombs?
We can measure it incredibly accurately.
Down to many decimal places.
Yeah.
But we can't derive that number from first principles unless we rely on these more speculative theories like GUTs or string theory, which aren't yet proven. That value determines the strength of the electromagnetic force itself via the fine structure constant. Why that strength? We don't fundamentally know.
So we've traced this amazing journey from Faraday's first hints in bubbling solutions to Millikan's incredibly clever oil drops, giving us solid proof.
Navigating the quark twist with their fractional charges hidden by confinement.
And seeing how theoretical physics, from Dirac's monopoles to GUTs, offers potential explanations for why charge might be quantized.
It truly is a cornerstone of modern physics. You can't build the standard model without it.
And yet it leaves you with this final thought to chew on. This basic property of everything, the force that holds atoms together and drives our technology, comes in these identical, perfect little packets. And the ultimate reason why nature chose that specific packet size, the exact value of E, well, that remains one of the deepest, most fascinating unanswered questions about the cosmos.